Mike, I had a question after we talked at your last lecture.
Okay.
We were talking a little bit about locking. It seems to be my favorite topic in your class so far. And talking about the issue that it would cause when you're doing octree refinement.
Mm-hmm.
Is it in some of those immersed methods, or are people going to treat pressure as an independent variable?
That is one way to so locking, because it's a stability question, and it usually means you have more constraints than you should. That generates a locked system. One way to recover that stability is to discretize the variables with the correct function spaces. So that would be a case where you would, for example, discretize pressure with one space and then maybe displacements or velocities with another space. That is one way to balance the constraints. There's a couple of ways there, but that's one of them.
Well, you mentioned using P refinement to handle it instead. So I was hoping you might mention a trade-off. Is it just an efficiency trade-off if you treat pressure as another variable or degree of freedom?
Those can be a little more expensive. They're also maybe a little more complicated to implement and maintain. But I would say one of the emerging one of the emerging ideas in the isogeometric community is that we're getting really good at handling higher degree without incurring a lot of additional computational cost. And if you can do that, then it's by far the simplest way to alleviate locking, is just increase the smoothness of the basis. So it's just simple. It's can work for every problem. You know, it just has some nice properties. Did that answer your question, Curtis?
Oh, sure. Thank you.
Okay, any other questions or comments? All right, today we're going to go over that last algorithm, which was the invert map algorithm. Let me bring up a whiteboard here. Somebody remind us what this algorithm was all about. What was the purpose of this algorithm?
So if I remember correctly, this invert map, it's kind of, instead of going from the parametric domain to our physical domain, we're going from our physical domain back to our parametric domain. So taking X and putting it into XC.
Perfect, Kenan. That's exactly what we're doing. So we've got, let's say, our flex domain. And this is our, what we call physical coordinates. And then we have some mapping that we're calling XF. And this is some nonlinear mapping. Right, and it's taking, so here's our X. It's taking, whoop, the crooked domain. Let's see. So it's taking coordinates from the XC parametric domain into this spatial domain. Now we have terms in our weak form where, for example, the traction term on the left end, right, we've got, let's change colors here. Right, we have our physical domain, let's say it's in here somewhere. So there's our CAD domain. And we're going to apply a traction at this point right here. at x equal to L. This is x equal to 0, let's say. So in our weak form, we had a term that was take all of the basis functions, the flex basis functions, evaluated at the physical coordinate 0 multiplied by our traction. Okay, now in order to actually do this integral, remember our basis functions, our flex basis functions, are defined, let's say, in the parametric domain. We were calling these, let's see, NA hat F is what we were calling these guys. And the NAs were just the NA hat Fs composed with the inverse of the map. Okay, so if we look at this term up here and we plug this in for NAF, what we realize is that what we really need to do is we need to take the inverse of our geometric map, right? So this whole term will be evaluated at x equal to 0 and then multiplied by our traction. So this here, this inverse is needed because it's in the definition of the basis functions in physical coordinates. So if we give you an x value, the only way that we can evaluate this basis function nf without the hat is to first map it through the inverse back to the place where the basis functions are actually defined, which is in the parametric domain. Okay, so it's this inverse that we're concerned with today, and that's why it's important. Even in 1D, you can see that it's necessary. And in multi-dimensions, it'll be even more critical. All right, so let's devise an algorithm for doing this. This is a nonlinear problem because the inverse of x is going to be a highly nonlinear function. So let me erase this and let's go ahead and start over here.
So on the term from, I assume that's coming from the PDE that we're
Yep,
trying to solve.
Yep.
Why was it evaluated at 0?
Oh, sorry. L.
Okay,
Yeah,
that's what I thought, but I just wanted to double check.
Yeah. Thanks, Ryan. Yeah, I was writing 0, and every time I wrote 0 in my mind, I was thinking L.
Okay.
There's a
To be
like.
clear, though, you do need it at 0 as well.
You do need one at 0.
We also have a constraint at 0, so you need to do it at L and 0.
Yeah. You guys were quiet for a long time, letting me just go on and on. Okay, so let's go ahead and derive an algorithm. And even though we're deriving this algorithm in this context, this idea of how we solve nonlinear problems through iteration is everywhere. So it's good that we're learning it very early on. So what we want to do, let's state our problem. Okay, so the problem is, okay, we want to find, given a coordinate x in omega c, find an xc in omega hat f such that x f of xc f, stick to my notation here, is equal to x. Okay, and the nonlinearity, it comes in this function, right? We can't there isn't a linear relationship between the values of x and the values of xc. There's no constants of proportionality. If there was, then we could just divide through by those constants and we would be done. But this is not a linear function. So how do we proceed? I mean, how do we solve this? Any thoughts, kind of, maybe if you don't know the answer already, what would you guess would be the way we would proceed?
So I'd assume that at least sometimes you could do it analytically.
Yeah, there may be cases where if this map is known, that you may be able to do it analytically. But in terms of our code, we want a scheme that works in every case, analytic or not. So for speed, though, I will say, if you know, for example, that this is like a linear map or an affine map, then you'd probably want to just hard code that in because it'll be fast. So our solution is going to be a very sophisticated one. And it's going to be guessing. How about that? We'll go ahead and guess. So what we're going to do is we're going to guess. And once we guess, we're going to have some way of determining how good or bad that guess is. And then we will update the guess in some smart way. Okay, so what we're going to do is we're going to take this function here, and let's write this left-hand side as a Taylor series. So we know that xf evaluated at some xc is going to be the Taylor series combination of x evaluated at some value xci plus dxf dxcf xcif delta xcf plus what we'll call higher order terms that we're going to ignore. We'll only go up to these these second terms here. And that better be equal to x. Okay. So since we threw these higher order terms out, we don't expect to nail the exact value because we don't have enough terms. So let's go ahead and rearrange these to give us an iterative scheme. And so we're going to guess and then we're going to iterate. So we're going to view little x as given known data. Okay, so that's been given. Let's go ahead and subtract this term over. So we get dxf delta xcf is equal to known data minus our current guess. Okay, and so let's go ahead and define this guy right here. Let's call it a residual, which is the common notation. Okay, the residual is how out of balance we are, how far away we are from the thing that we're iterating towards. And so now what you can see is by taking a Taylor series expansion, throwing away higher order terms, what we know is that we can put in a guess here. The residual will be non-zero, but then what we're going to do is we're going to solve for an update, delta xcf, that will push us in the right direction of this, in the direction of this gradient term here, right? So it's going to move us at least in the direction of the derivative, which makes a lot of sense. So this scheme has a name. I'm sure you've heard it before. It's called Newton-Raphson. Okay, Newton-Raphson says, given, in this instance, we would write it, given a guess, let's call it xc0 of f. What we want to do is we want to solve our linear problem here. And so I'll make a comment about this in a minute. Let me write this down. We want to solve this for the increment. Now, what you like about this is that this is a linear problem. Notice that a derivative is always linear. So what we've done is we've swapped out a nonlinear problem for a linear approximation. And the linear approximation, right, we have a constant plus some slope, this derivative term, and then an increment. And so we have swapped out a linear problem that we can't solve analytically for a sequence of linear problems that converges to the exact solution. So we solve this guy for delta CF, and then we update our guess. So we have xci plus 1 of f is going to be equal to xci plus delta xcf. And we should put some kind of a check. So we should check for convergence here, right? And usually what we do is we'll take, I need a little more space here. Maybe I'll just, yeah. Let me go ahead and erase this line. So let's put the check. Let's put this second line up here where I've got a little more space. So what you'll do is you normally will check for convergence. And what that means is the norm of the residual small? Okay, and we will define what small means, and we'll also define what the norm means. Oftentimes you'll take maybe a scaled norm where you'll take the norm, a relative norm like this, right? So are we getting small in comparison to our initial residual? Anyway, there's no like one way to compute, to answer the question, is the residual small? There's a lot of different ways. And in sophisticated codes, there will be a whole sequence of residual convergence checks that will be undertaken in order to determine if things are small enough to proceed to the next kind of time step or load step. Okay, any questions on this up to this point?
So I have a question. What if you had another higher order term, so like dxf, and anyway.
Yeah, exactly. Yeah, great question, Rebecca. Because you're throwing away all the terms that are what I would say quadratic and higher, right? So we have a constant, a linear, and then all the quadratic and higher terms are thrown away. How fast do you expect the residual to go to 0, given the information that we maintained, that we didn't throw away?
I expect it to be going to 0 linearly.
Oh, so it actually it'll go at a quadratic rate.
Oh.
So yeah, so it'll go at a quadratic rate. Newton-Raphson always converges quadratically.
Cool. If you added other terms, would it do cubically?
Yep, that's right. So the question might be, well, why does Newton-Raphson tend to stop here? Anybody have any ideas? Because you could just add a whole bunch of terms.
It simplifies the solve, doesn't it?
in general, the most expensive part of your nonlinear iteration will be forming this gradient. Admittedly, because we're in one dimension, everything is fast, right? But in general, this thing is going to be a massive matrix. In fact, it'll be what we call the stiffness matrix here. What we'll see later in a nonlinear setting, this is actually what the stiffness matrix is in the context of continuum problems. But this gradient is normally very expensive, and so we get the biggest bang for our buck in some sense just by taking this first derivative and stopping there. It'll give us kind of the best approximation in some sense.
Yeah, I would add it's not only is expensive to form, but it's often very difficult to formulate. Far more difficult than the residual. So going and adding more higher order terms sounds like a nightmare.
Yeah, we call this thing, we'll come back to this in the context of continuum problems, but for those of you who have been in this world, we call this the consistent tangent. And the term consistent comes from the fact that it's consistent with this Taylor series. There's lots of things people do to make this more efficient, but for big problems, like you can barely, I mean, even figuring out how to write down the consistent tangent. Remember, this is a simple derivative with respect to a real coordinate. In a general theory, this is going to be a variational derivative of a very complicated nonlinear theory. And so, I mean, my PhD students who have been with me for a while, we spend a lot of our time just deriving consistent tangents. Although I will say that we're actually, and some of the labs people may be tuned into this, but there is a technique called automatic differentiation, which is, in my opinion, if you were to write a code from scratch today, you'd probably want to take a really hard look whether you could just use automatic differentiation, and then all you have to do is give the residual to the algorithm and it will generate the differentials for you automatically, and so you don't have to derive consistent tangents. I think historically the knock against, so in all the big traditional FEA codes, most tangents are derived on a piece of paper and then typed into the computer, because you can make all kinds of, you understand exactly what it is, so you can do things for efficiency. And so the knock has been that automatic differentiation might not be as efficient. But I'm hearing rumbles from people who do this that may not be true anymore. I'd be curious if anybody on the line has any experience with that.
So we use automatic differentiation in Plato.
I was thinking of
and-
Plato. That's a place it's been used heavily. But
Yeah, I'm really not an expert on this, but the story that I've taken away from it, Miguel and Josh would be the people to talk to, but basically, like, they say that one of the big reasons that automatic differentiation has been looked at as being really slow is because implementing it in like traditional FEA codes and like going through the loops that are traditionally gone through in FEA apparently complicates the process, whereas if you loop through things differently, then you can do it efficiently. That's kind of the gist of it. And yeah, I really don't understand exactly how that's done, but it's quick in Plato.
Yeah.
If we have some of the INL folks on the line, I know that the Moose finite element code heavily relies on or utilizes automatic differentiation. So I think I saw Fande is on. Maybe
Yeah,
maybe he or someone else could
I
talk
think
about
Alex
that.
Lindsay is on. He's probably the best one to talk about that. But yeah, we are in the process of extending an automatic differentiation capability across the code. I mean, if you've worked out by hand what the Jacobian is, it's always going to be faster to use that. But in a lot of, it saves a lot of effort if to use automatic differentiation if it's very difficult to form that or you can't do it easily or whatever. Yeah. I don't know if Alex wants to chime in. But,
And I think, part of the strategy with it too is that, similar to how we've talked about the time for end users on, trying to build a mesh, maybe spending months building a mesh just to then run it in a day or two, that's like an area that if you could drastically reduce that much time or that amount of time, then you could do more analyses. And so what I've heard also is that it's just so much easier to then be able to implement some new physics and then use automatic differentiation to do this for you, rather than having to spend months or years deriving what the consistent tangent is, right? And so it lets you, you sacrifice some computational speed for just being able to solve problems.
exactly.
As soon as possible.
Yeah, forming the Jacobian would be the analog to making a mesh.
Yeah, I mean, well, we'll do it later. When we get into maybe next semester, we'll do nonlinear elasticity and we'll spend like 3 lectures just deriving dx, dxc for that theory. And however, I will say that good mechanicians should be good at this because understanding how parameters change in the context of differentiation means that you understand your theory. So, but there are like some cases where if you've got like a lot of different physics going on at once and you can couple them together in all kinds of different ways, it just may not be practical to sit down and derive every possible combination. So, but I mean, like at core form, we're also kind of investigating whether or not, I mean, I think we'll always have, for the theories that we understand, we'll always just write down the consistent tangent, but it's really nice, even from a debug standpoint, to have an automatic differentiation capability, because you can derive your consistent tangent, but they're so complicated and they're very difficult to debug when you get them wrong. So it's nice to have something that tells you whether you're even close or not. Because the only thing that you'll know a lot of times, if you implement a consistent tangent and you run it, you will converge most usually, but you just won't converge quadratically. And that's it for your errors. So it can be difficult. Like you can have a minus sign off or a factor of 2 and you will not converge quadratically. It has to be exactly correct or else you'll get sub quadratic convergence. So that's an important.
And I might make one other comment too, just on the value of stopping at the first derivative and getting quadratic convergence, is that you can make up just some toy examples just to look at like iterations required to converge to a certain value. And in some cases, it might be to go from linear convergence to quadratic might be a rate increase of 41 times, whereas going from quadratic to cubic might only be an additional 60%. It's like only 1.6 times faster. And so it's just not worth the effort to have the higher order terms.
Okay,
from a diminishing return standpoint.
Yeah.
Can I ask a question about that, Greg?
Sure.
So what about when you do automatic differentiation? If you do automatic differentiation, are you able to get those higher order terms with less investment?
That I don't know about that.
Yeah, can you differentiate to any order? That's a good question. I do not know either.
Yeah, I know that one of the issues with I think one of the issues with automatic differentiation too is that you have to have different data types, because now, as opposed to having a single, like a double, you have to have like a double double almost. So it's because you have to be able to carry around the value and its derivative on every calculation you're going through. So it's just from a compute complexity standpoint, it's kind of like going from having real doubles to complex doubles. But I don't know about the higher order terms, stuff like that. Like if that would require like a double 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 or something, I'm not sure. But conceivably that might make sense.
Yeah. You know, Ryan, you may want to ask one of your colleagues. I would be interested in having them present on a Friday something along these lines, because I think, at least for me, it would be quite informative for my group to see where that technology is at.
Yeah, I'll talk to him about that. We might want to ask somebody that's on the Sacado team too. That's the code that we use for automatic differentiation.
Yeah, great. Yeah. Well, not a big deal, but just it would be nice. I'd like to know more about it.
Yeah.
Okay. Great. Let's like, it's nice to see all the algebra, but let's just like do it graphically so you can see what this method is doing. Let's just do a little example by hand here, just schematically. It's all about the slope. So let's say we've got C here, and then the y-axis is x f xcf. Okay. And let's say our residual function, or basically, well, the plot of xf, the map, let's say it looks something like this. So it's not linear, it's not crazy either. And so let's walk through what Newton-Raphson does. Okay, so the first step is we're going to guess xc0. And usually, a lot of times you just set it equal to 0. Okay, so there's the guess. Okay, so then what do we do? Well, we measure, we put together the residual. So the residual is going to be, oh, and let's say that little x is maybe right here. Okay, this is going to be our little x value. So okay, so we measure the residual, and the residual is nothing more than little x minus x the C0F. So it's this distance right here. Okay, and then we develop the consistent tangent. So dr, well, I guess this is a constant term, so it goes away, but let me write down according to the notes I just did here. dxf dxc at xc0. So what is the slope at xc0? Remember, this is like rise over run. And then we're solving for a delta d, which is going to be a run. So we're trying to figure out, using this slope, comes up like this, maybe. Pardon my handwriting, it's not great. Okay, so we're going to try and compute that. So we compute delta D is equal to our residual at xc0. Okay, and we solve for delta D. So in this case, our delta D is going to put us here. We do an update, xc1 is equal to xc0 plus delta D. So that's going to maybe put us here. There's xc1 of f. Okay. Am I doing delta D? No, I'm doing, I keep switching notation on you guys. Sorry about that. Okay, so that's what the first step looks like. And then we just repeat. Okay, so we measure now this residual here. It's our next residual. And then we compute the tangent, which puts us maybe here. And then that gives us C2F. And do you see how fast it goes to 0 if your function is smooth? And there's our next residual right here. And we take our next guy here. And then you can even see in this simple example, the residual converges very quickly. So it's going to be in this example, maybe 3 or 4 iterations, and you're going to be basically at machine precision for this smooth function. So this tells you something important about Newton-Raphson iteration. Let's just maybe jot down some of these important properties or observations. Under what conditions is it going to work well? What are some things we can say about it? What are some of the conditions where Newton-Raphson is going to be like a reasonable?
If the map is invertible to begin with.
Okay, yeah, that's important. Okay, so we assume that it's invertible. Okay, perfect. Okay, what else?
So that also where the 0 is, or where you're trying to converge to, there's not a lot of oscillations in that area. So you're close to the
Okay.
to the root.
Yeah, so the initial guess should be close to a solution. Okay, so what Greg is saying is, if we were to zoom out on this function that we've plotted here, and in the zoomed out picture, like let's say we zoom out 1,000 times, and you know, when we zoom out, the function actually looks like, you know, like that. Then if our solution we're looking for is way over here, and then we start here, there's no way we're going to get through all of these local minima and maxima. We're going to end up shooting off. The slope, for example, is going to end up shooting us all over the place. And so Newton-Raphson works well when you're already pretty close to the solution. So that means that the initial guess is best if it's an informed guess. Okay. What else? There's one other thing I'm thinking of that you can see in this problem that's important.
Your solution is continuous?
Yeah, so the solution, so this x, this map or the function that we're iterating on, it should be smooth. So the function is smooth, because at least it better be differentiable, right? If it's not even differentiable, then what does this even mean when we take the gradient of x, if x isn't even differentiable? And so,
and continuously differentiable too.
yes, that's right, because you're assuming that this Taylor series even exists, even though you don't use all of the terms. So let's talk a little bit about this. In mechanics, there are a lot of smooth phenomena, but there's also a lot of phenomena that's not differentiable. The one thing that sticks out in my mind is contact between two bodies. That is not a smooth phenomena. Nevertheless, we solve it often using these methodologies. And so what's often done is you will take a theory and you'll actually go through a process of what I would call smoothing it out. meaning you may actually change the theory slightly in order to smooth out the quantities that you need to differentiate, just enough that you can recover the appropriate rates of convergence in kind of a Newton-Raphson setting. In the case of our function, which is always just linear combinations of smooth functions, this should converge really well. And in fact, what you'll see when you code this up in even in 1D, if your map is nonlinear but composed of smooth functions, your Newton-Raphson iteration will converge to machine precision in 1 or 2 iterations often. I guess 2 or 3. If it was 1, that would be either a lucky guess or it would have to be linear. So inverting the map in the context of this flex representation method, when we know so much about the input function, is one of the nice characteristics of the method, that this inversion, although on the face of it looks like a complication, it actually converges extremely fast once you get on the right element or get close to the solution. And so I'll have you guys implement a little invert map function. So this is what in the notes I have a kind of pseudo code description. I think I call it invert map, and you pass it an X value, and I believe like all of the basis function. I don't remember exactly what it is, but and so you're going to take this and develop this algorithm in the context of this particular map. Okay, and what I will say about finite elements in particular in the nonlinear setting is that this is the way that this is ubiquitous, this idea of linearizing quantities. Anytime you have a nonlinear problem and you read the literature and you look at how people are solving it, once you understand this idea of linearization, it will make a lot of the literature more accessible, because those techniques are everywhere in computational solid mechanics and computational mechanics in general. So even though we're doing it in this little toy problem, this is a very foundational concept that will be used over and over and over again. Okay, any questions or comments on that?
So I do have one just final comment. And this is something that I've seen trip up people before or cause questions. So maybe just to head it off, the nonlinear function that you've drawn is not actually known to either the person solving it or the code itself, right? Only like the nonlinear function that you've drawn there is if you were to evaluate it on all those points, but those are expensive. So like only an all-knowing being actually knows what that nonlinear function is. And so we're trying to make these linear approximations and then are querying what the value is of that nonlinear function at that point.
We only know this value, and this value. We actually don't know anything in between, right?
Right.
And so that's correct. So let me just tell you about this. Let me just make another comment. I actually, before I say that was it Ryan that were you about to say something, or somebody
Eric
else?
Dodge and I was about to just say this process that we just did here, this was for defining our XF of XC. So this is not looking at the inverse quite yet.
No, this is how we compute the inverse, because I give you an X, and then this algorithm will tell you what the XC value is. That is the inverse map. Right? We have this map, but we want to go this way, which says, give me an X and I'll give you the corresponding XC. So I give you an X, then you iterate until you converge on big C.
Yeah, Eric, we know x of f of xc because it's just the evaluation of your basis functions at xc multiplied by your nodes. So you know how to compute that. If you give me an xc, I know how to compute the x value associated with that, but it's a lot harder to go the other way.
Okay.
Yeah, by construction, we know this function because we defined it. We wrote it down. So there's no question about this one, but we never wrote down the inverse. We just know that it exists.
Right. It's kind of similar to if you just look at the function x squared, that if I tell you x is 3, you can just easily find that x squared is 9. But if you start with that the value is 49 and tell me what x is, that there's not like a simple, oh, just multiply it by itself sort of thing to find out what initially was. You have to do like a nonlinear solve to find the value. That's maybe like a very simple version of what's happening here, but
Okay, so let's just make one last comment about this initial guess. This is actually a pretty important point. We need a good initial guess. So in the context of our problem, we have this domain, call this our omega c, and then I give you some x value. And now down here, you can see just graphically, I'm in the first, second, I'm in the third element. So would a good initial guess be something in the first element? Is that a good idea? What do you think?
Sometimes you ask questions that are obvious enough, I just want to say the wrong answer just to be a nugget.
You can do that. That'll spice things up. So the point I'm trying to make is that there should be a pre-process. Sometimes we call it a spatial filter, which narrows down the search, right? So you should be able to say, given this x value, at least you should be able to determine which element you're in. And so then once you know what element you're in, really you can take any value you want. Maybe you just take the midpoint value for your initial guess and it will find the right value. And so in your little algorithm, there should be a little spatial filter that maybe determines what element am I in. And then once you know what element you're in, you do Newton-Raphson on the guess. And this, you could write a whole book on this right here for complicated problems, but in this setting, I'm just exposing you to the issue. And you should be able to write it down in just a couple of lines of code for this one. Okay. Any other questions or comments? If not, we'll end for the day. Okay, well, any students that want to chat with me can hang on. Otherwise, we'll end for the day. Thanks, everybody.